All right. So last lecture, as you may remember, we introduced automatic speech recognition, and you saw that we can create a model from each utterance. If you have an utterance, you can create a spectrogram from it, and from that spectrogram, you can create a model, and then you can test each of the models against each test utterance using the dot product, using the cosine distance, which is essentially the dot product. And so what we want to do in today's lecture is essentially carry that forward to create new kinds of models using the PyTorch library. We're going to create neural network models. Neural networks are, well, let's look them up. A neural network is a neural
I have
network.
a question, sir.
Yes, please.
Okay, so some of us have backlog, right? So whenever we decide to do the homework,
Hmm.
so we don't have the instruction that what we're supposed to do. Maybe we have to go through the videos, lecture videos, the entire lecture videos to understand that what the homework is for homework two, homework three or four or something like that. So would you kindly uh, give us a title or instruction that what we have to do for this for the particular homework because the title is about like uh, paste the link here. So it's a little bit
Hmm.
tiring. So if it's possible, I know it's my mistake that I have backlog, but is it possible? Please kindly share the instruction that what do you specifically do for a particular assignment anyway.
Yes, certainly. The course, the lectures are on the YouTube channel, which you can access by going to the Canvas webpage and then scroll all the way down to where it says lecture videos. And if you click on lecture videos, it will take you to the course YouTube channel where you can see recordings of all of the past lectures.
Yeah,
So,
yes, but well, I say that whenever I uh, want to see the instruction that for a particular homework, what the specific task is for me. So there's
mhm.
nothing written there.
Yeah, so for example, if you want to see the how to do homework 7, you go to Intro to Speech Understanding Lecture 7, and then you can
Yes.
watch that video in order to see the instructions.
So it's
Let's see if
okay.
Jupyter will work. I've been changing some things in my
So
computer
you can
settings,
see
so I
that
hope
here
that
that
lecture 7 goes through the entire lecture
we have a
7
cosine with
video,
four complete
right?
periods.
And if you
And in the
wanted to see
frequency
how to do
domain,
lecture
we have
7,
a
then you would
discrete
just
cosine
go
transform
through
that
the
has,
video, and it will show
let
you.
me,
Um, in each lecture video, I've recorded detailed instructions on exactly how to do the homework. If you want to, if you want to see the homework, of course, you can look at it. If you don't want to see the instructions and you just want to see the homework, you can see the homework by going to the GitHub webpage, which is here. And so for lecture 7, for example, you would go to lecture 7, and then you can look and see the homework is here in detail, and the lecture the Jupyter notebook that describes how to do the homework is here.
Thank you very much. It's my mistake that I didn't notice it properly.
Okay, yeah. So that all of that material is available for you easily online through the Canvas webpage. Right. So today we're really learning about neural networks. Neural networks are the backbone of artificial intelligence. Right. So a neural network is a network that looks like this. Each of these layers is a dot product. Right. So every one of these nodes is computing the dot product between a set of weights and the input activations. So we have this NumPy dot, right, that we've been using, the NumPy dot product. And that NumPy dot product now is going to get stacked up into multiple layers in order to create, we'll create, NumPy dot product takes the dot product of two vectors, A and B, and every one of these circles is a NumPy dot product. So this circle is computing the dot product of a set of weights with the inputs. This circle is computing a different dot product of a set of weights with the inputs, and so on. For each of these circles is computing the dot product between a set of weights and the input vector. All of that can be done for you automatically using the PyTorch toolkit. And so what we're going to do today is install PyTorch and use it to create a relatively simple, use it to create a two-layer neural network exactly like this one. We'll create a two-layer neural network like this, where the input will be a spectrogram, and then it will have one hidden layer, and then the output will be the recognition. So the PyTorch is a toolkit specifically for the purpose of learning of neural networks, and it does all the way up to large language models for computer vision and for speech processing. Today, let's do that by starting Jupyter. So just go ahead and start up the Jupyter Notebook. Maybe I should do that from a terminal. Let me open a terminal here and start up Jupyter Notebook. All right, it's not loading the files for some reason. That's strange. Let me cancel it and try running it again. Oh, that's because I'm in the wrong directory. I want to go to my home directory. All right, and in my home directory, let's start up Jupyter Notebook, and that will allow me to search for the place where I have the lecture materials. Using the methods from lecture one, of course, I've downloaded the lecture materials and I put them into this folder called KCGI Intro Speech Understanding. And so today I want to go to lecture 10 and open up the lecture 10 notebook. And today we're going to do neural network speech recognition. For example, you can go and look at the Wikipedia page for information about neural networks. And neural networks really involve three things: data pre-processing, training the neural network, and testing the neural network. Data pre-processing means you take all of your training examples and partition them into waveform X and the label Y. So a set of waveforms and then a set of labels. And this is just like what we did last lecture, right? In last lecture, we had 5 example waveforms, 5 training data. Those were the vowels A, E, U, A, O. And so we had 5 examples, N was 5. And for each of those, we had the label that we wanted it to produce: A, E, U, A, or O. And so we're going to do, for data pre-processing, we're going to basically be doing the same thing that we've been doing for the past 2 lectures. We're going to load in the waveform using Librosa, and it's going to produce a warning message because Librosa is using this outdated package. But it reads it in, and just to make sure I can plot the spectrogram, so I will create the magnitude short time Fourier transform by chopping it into frames, and then by taking the FFT, and then by taking the absolute value, and then I'll create the spectrogram by taking only the first half of the frequency coefficients for every frame, and then in every frame I'll take the maximum of 0.001 times the maximum amplitude of the spectrogram, or MSTFT, and I'll take 20 times the log base 10 of that. And that will give me a spectrogram that shows the vowels that we saw last time: A, E, U, A, O. Let me also add let's import IPython display, and let's do IPython display dot audio speech with the sampling rate fs, just so that we can listen to it and make sure that it is what we thought it is. Okay, um, I've got the syntax incorrect for some reason, so let's look up IPython display audio and see exactly what the syntax should be. Um, from IPython.display import audio. That looks like the same thing that I just did. From IPython.display. Oh, I bet it's capital I, capital P. All of the other letters are small, and then capital A audio is large. All right. From IPython.display, import audio and display, and then audio data equals speech and rate equals rate. Oh, I see it. It expected that fs might be something else. So I just need to specify that this is rate. There we go. Now we can listen.
A, E, U, A, O.
There we go. All right, so we have the so we know the waveform. We have this waveform that has the five vowels a, e, u, a, o, and from this, just like last time, we want to create five training examples that will be labeled with the labels of the five vowels. We'll say that the silence is y equals 0, and y equals 1, 2, 3, 4, 5 will be the vowels a, e, u, a, o. And so we can do that using the same thing that we did last time, using a voice activity detector, where we'll create frames with 25 milliseconds and with 10 milliseconds in between them. We'll calculate the energy in each of those frames by summing up the square of the frame, and then we'll say that that there's speech there if the energy is greater than 10% of the maximum. And from that, we'll calculate the start frame of every segment and the end frame of every segment. And then um, from 5 times the start frame to 5 times the end frame, we'll label that as A, E, U, A, or O. And we're going to do that from 5 times the start frame up to 5 times the end frame. Why is that? Because the energy is done with a frame length of 25 milliseconds and a skip of 10 milliseconds, and because the wideband spectrogram, the model that we're going to create, will have, instead of 10 millisecond skip, it will have a 2 millisecond skip, right? Have we, oh, we use a 10 millisecond skip for VAD, but only a 2 millisecond skip for the spectrogram. So every VAD frame needs to label 5 frames of Y. So we haven't created X yet, have we? Oh, here we have, yeah, we have sgram is going to be the X. And this is calculated with a 2 millisecond skip. So the data is calculated with a wideband spectrogram with a 2 millisecond skip. The VAD is created with a energy that has a 10 millisecond skip. And so every time we have a start frame, we'll go 5 times the start frame in order to say where do we start in the spectrogram. And then I'll label each of those with a number specifying which vowel it is. 1, 2, 3, 4, 5. The ones that are not specified will all be silences. So all of the silences in between will be labeled as 0, and then the segment where the vowel is will be labeled 1, 2, 3, 4, or 5. So you see we have silences are all 0, and then vowel A, E, U, A, O are being labeled with this label sequence, which is the Y, right? Here's X. X is the input spectrogram. Here's Y. Y is the output label, which is either 0, 1, 2, 3, 4, or 5. Now that we have every frame labeled, now we want to train a neural network. Essentially, we're creating a model of each of these vowels, just like we did last time, right? So going back to Wikipedia Neural Network, basically for every vowel, we want to create a different one of these label of a different one of these label circles that's a different dot product with the input. But now rather than estimating this model using the average across the entire waveform, now I'm going to use all of the frames. look from 500 up to 700, we have all of those are frames of ah. So all of these 200 frames of this spectrogram, these are all examples of the vowel ah. And we want to use all of these 200 examples in order to help us learn what ah sounds like. And all of these 200 examples in order to help us learn what E sounds like. Right, so we're going to use a neural network that will look at all of these 200 examples, 200 separate examples of training data that we have now for each of the vowels. And we'll do that by taking this entire image as X. Every single column in here is an X. So now instead of just 5 examples for X, now we have 3,000. You can see that this frame index goes up to 3,000. So now our training data is going to be X1 through X3000 instead of X1 through X5. And our output labels, Y1 through YN, that'll be Y1 through Y of 3,000. So the training labels start out with Y of 1 and go all the way up through Y of 3,000. So in this way, now we have 3,000 inputs and 3,000 outputs, and we want to use those to train a neural network. We're going to train the neural network using the PyTorch toolkit, and you need to download that. You can download it by using the exclamation point and then pip, right, in order to run pip, in order to install Torch and Torch Vision. So this will install the standard neural network training package is called PyTorch, and it allows you all of the interesting machine learning and AI research is done using PyTorch, and so it's worthwhile to install it and to learn a little bit about how to use it. PyTorch is very complicated to use, so today we're only going to do a couple of very simple things with it. Mostly we're going to create this cosine distance that we used last time. Right? This equation that you see in the screen is the cosine distance that we learned about last time. We take a model, W sub I, and we calculate the dot product between that model and the input x vector. And then we normalize by dividing by the absolute value of x and the absolute value of w. We can do that using 2 steps in the neural network. The first step is using a layer norm, which divides by the absolute value of x. So the layer norm takes x and divides it by its absolute value. This is a standard package in PyTorch. It's part of, so you can see torch.nn.layernorm. It takes the output of the layer is x minus its expected value divided by the square root of its variance. And so this is exactly right, x divided by the absolute value of x, right? The second layer calculates the dot product between x and each of the rows of the matrix A. So the second is a linear layer. The linear layer calculates x times A transpose, where x is a row vector, or A times x, where x is a column vector, right? So it's the matrix multiplication between x and A transpose, or between A and x. And what this does is it calculates the dot product between x and each one of the rows of the matrix A. So if the matrix A has rows W0 through W5, and if we've already normalized the matrix A so that each row is divided by its magnitude, then we can just use a linear layer to take these dot products. So basically, we're going to train exactly the same kind of model that we had last time. We'll use the cosine distance, and we'll use the cosine distance in PyTorch by creating first a layer norm and second a linear layer. And these will all be put together inside what's called a sequential object. A sequential object is just a sequence of different operations. So here's where we're going to use the really strange PyTorch syntax. We're going to import torch neural net, and then we're going to create a torch neural net sequential object. And that sequential object will include, first of all, a layer norm, and the layer norm will have a 16-dimensional input. That's because this spectrogram is 16-dimensional, right? So each of the x vectors is 16-dimensional. So the layer norm has to have a dimension that specifies the input dimension of x, which is 16. And then we'll have a linear layer. And the linear layer will go from a 16-dimensional input to a 6-dimensional output, W0 through W5. And that corresponds to the number of different values of y that there are. Right? We have 6 different possible outputs. Y can be 0 for silence, 1 for ah, 2 for e, 3 for oo, 4 for a, and 5 for o. So we're just going to do exactly the one layer neural network that we did last time, where we do a cosine distance, but we're going to do that using a layer norm with a 16-dimensional input, followed by a linear layer with a 16 by 6 weight matrix. And this is implementing exactly the same classifier that we did last time, but now we're going to train it using PyTorch instead of training it by just averaging. Right, so we're going to train it using what's called the cross entropy loss. Here's a description of cross entropy. It just calculates the negative log probability as estimated by the neural net. This is a good way to classify to determine how good the output of the neural network is. It's calculating the probability that y is equal to k given the value of x. And that's calculated using this what's called a softmax function, e to the z sub k over the sum from I equals 0 to 5 of e to the z sub I, where each of the z's is that cosine distance that we learned last time. So instead of training it by just averaging the way we did last time, now we're going to train it using the cross entropy loss in PyTorch. Now there's a whole lot of things that we need to put together in order to make this work in PyTorch. First of all, we define the loss function is the cross entropy loss. Second, we need to define an optimizer. We can use stochastic gradient descent or ADAM. It actually doesn't matter very much which optimizer we use, but there's one called ADAM that's a very good choice for optimization. So we'll create an optimizer and we'll feed in the parameters from our model. Remember, the model is this. The model is the sequential model that has layer norm followed by linear. That model is going to be the input to the optimizer. And then we'll create a sequence of loss values, and our goal will be to try to reduce the loss. The loss is telling us how good is, how good is the probability, right? If the negative log probability should be small, that means the probability should be large. So the smaller this loss becomes, the closer to 0 it is, the better and the closer our probability is to 1. And then we'll do 1,000 iterations of training. For each iteration of training, we'll take the model and we'll apply that model to the spectrogram. The spectrogram is, right, all of our examples of X. And then we'll compare that output Z to the labels, which are what the labels should, what our desired output. And here's our actual output. So we compare our actual output Z to the labels, which are the output that we wanted to get. Notice that we have to turn each of those into a torch tensor. We take the spectrogram and turn it into a torch tensor. We take the labels and turn it into a torch tensor. I'm not going to go into a lot of detail about why, but that's just this extra step that we have to do in order to make things work in PyTorch. And then we have to take that loss and get out a NumPy value. We get that NumPy value using the item method. So we call loss.item in order to find out what the loss is, and we list it as loss values of t. All right, now we've calculated how good the neural network is. Now we want to do this backward operation. What the backward operation does is it updates the model. It says from the loss, go backward and take one optimizer step in order to update the model, in order to improve the model. And the result then, it will, I did import torch, didn't I? No, I haven't yet. Here it is, import torch.nn and create the model. Now I've created the model. It has a layer norm and it has a linear layer. And now I want to train the model by defining the loss function and by defining the optimizer, and then by taking 1,000 steps of this training. So the neural network training is going to run for 1,000 steps, and we see here's the cross entropy loss over the training iteration number, and the training iteration is improved in every iteration for 1,000 steps. Remember, the training loss is the negative log probability. So when the probability becomes 1, then the logarithm becomes 0. And we're getting pretty close to that. The logarithm is getting down to 0.5. It's not quite zero loss, but it's getting much closer. Now we can find out how well it worked. Let's apply it to the same spectrogram, to the same X. We'll take that spectrogram and turn it into X, get Z, which is the output of the dot product, right? It's the layer norm followed by the linear layer. And then we will plot the spectrogram in one plot, and in the second plot, I'm going to plot I'm going to take the Z functions and pass them through that softmax, pass them through this nonlinearity in order to calculate the probability, and plot the resulting output. And the resulting output you see is 0 during the first silence, and then it's 1. So this is taking Z and passing it through the softmax. Z is a 6-dimensional vector at every time step. And that 6-dimensional time vector I'm turning into a probability. And you can see that this probability is maximum for A during the A segment, maximum for E during the E segment, maximum for U during the U segment, for A during the A segment, and finally for O. So we're using PyTorch to do exactly the same thing that we did last time using NumPy. Remember, all that we're doing is this basic dot product classifier. We're taking each of the models, one model for every vowel, take its dot product with X, and then we try to find out which one is maximum. And which one is maximum we're doing using the softmax. And so the calculations here are exactly the same calculations that we did last time. And this time it's hard because we're using PyTorch, and PyTorch is complicated because it has so many different features. Right? So really the main thing that we're learning this week is just how to use PyTorch to do something that you already know how to do. So here we've tested the neural network on the training data, and it worked well for the training data. If we want to run it on test speech, then we need to load the test speech utterance. So let's load the test speech utterance, and if I listen to it,
E ah oo a o.
So it's 7 vowels in a row, e a, oo, a, o. And we want to use the neural network model that we've just learned in order to figure out which vowels were produced. Right? So we want our neural network to be able to understand it. So first we have to turn that input into a spectrogram. It needs to be a 16-dimensional spectrogram, right? And so we calculate this spectrogram, and now this spectrogram we're going to feed into the neural network. So we have e a, oo, a, o, and then there's some noise here at the beginning. I don't know what that is. And then the idea will be that the neural network will take each one of these columns and pass it into the neural network and get as output something that looks like this, a column telling it which vowel is being produced in that frame. And hopefully it will get the right results. So we take that spectrogram and pass it through the model. Right? And we get our test results. Our test results are the dot products. In order to turn the dot products into probabilities, we pass them through the softmax and then detach them from and turn them into NumPy and then transpose them so we can create an image. Right? And then we'll just show them in the image, and we see, in fact, E, A, oo, a, o. It mostly got it right. You can see it's bouncing around a little bit. In the E, sometimes it mistakes the E for an A. In the U, sometimes it mistakes the U for an O. In the O, sometimes it mistakes the O for an A. You can see that if we zoom in here, the probability is strongest for O most of the time, but in some of the frames it's stronger for A, and in some of the frames it's stronger for which one is this? For U, right? It's bouncing around between O, U, and A. And so we're getting the neural net is getting the result right most of the time. And really what we're doing is just kind of doing exactly the same calculations that we did last time, but using this PyTorch syntax where we create a model that contains the normalization, the layer norm, and the linear layer. And then we apply that model to the spectrogram. And then we take the results and pass it through a softmax in order to tell us which vowel is being produced. The homework is doing all of those things. The homework basically will have three functions to write. The first function will be the data preparation. The second function will be the training, and the third function will be the testing. So each of these is one of the sections of what we just did. So for the getting the features for the training part, right? What we want to do is we want to take in a waveform and a sampling rate, and we want to have as output the features, which is the spectrogram array, and the labels, which has the same number of frames. And we want to do that by calculating the voice activity detector with a 10 millisecond skip and the spectrogram with a 2 millisecond skip. So let's say the X window length is 0.025 times fs, and the X window skip is 0.01 times fs. And for the VAD window length, oh, I'm sorry, those were the VAD ones. The X is going to be 2 millisecond skip. The X window length is 0.04 times fs, and the X window skip is 0.02 times fs. Right? Now we want to create frames using each of those two varieties. So the VAD frames are NumPy array of waveform from M to M plus VAD window length, or M in the range between 0 and the length of the waveform minus the VAD window length, with a skip equal to the VAD window skip. All right, and then the X frames will be the same thing, but with the X window length and the X window skip instead. All right. Now let's see. From the VAD, we want to create an energy. We want to calculate what the energy is in each of those frames. So we want to calculate the sum of the square of each of the frames. Let's say VAD frames of M colon M colon. And actually, we just want to square the VAD frames, and then we want to calculate their sum along the, let's see, we've got the row dimension is the frame, so we want to calculate the sum along each frame like that. And then the VAD is going to be, the voice activity detector will be 1 every time that the energy is greater than 0.01 times the maximum, right? Is that what we say up here? Give every non-silent segment a different label. So VAD is energy of M greater than 0.1 times the maximum energy. All right, and then we want to find the start frames. Start frames are the frames such that the VAD of M is equal to 1, and VAD of M minus 1 is equal to 0, or M in the range between 1 and the length of the VAD. And the end frames are the opposite. The end frames are the places where the VAD goes from being 0 to being 1. I mean, from being VAD of M is 0 and VAD of M minus 1 is 1. All right, and now we have the start and the end of every segment, and so now we want to find now we want to create a set of labels, which is n frames long. It should be as long, have as many frames as x. So as many frames as x. And then for every one of these segments, we want to go from the start frame to the end frame and give it a new label. So for k in the range of the length of start frames, we want to take labels from 5 times the start frames of k to 5 times the end frames of k, and we want that to equal k. Right? So we've gone through, and the first segment is going to be labeled 1, and the second segment will be labeled 2, and the third segment will be labeled 3, and so on. Now we've used the energy and the VAD to create the labels. Now we want to actually create the features. The features will be the spectrogram. So the feature, the MSTFT will just be the absolute value of the FFT, of the X frames, and we'll be taking the FFT along the second dimension, and then we'll be taking the absolute value of that, and then we want to take the feature vector, feature matrix will actually be the spectrogram. So let's say the FFT length is equal to MSTFT shape 1. That's how many features there are, how many frequencies there are. And then we want the features matrix will be the 20 times the log base 10 of the maximum of either 0 or, of either 0.001 times the Amax of the MSTFT, right? We're going to clip it at 60 decibels below the maximum value, or MSTFT. So we clip it at 60 times the maximum value. And the other thing that we want to do is we want to make sure that we keep only the first half of the frequencies. So we want to keep the frequencies from 0 up to FFT length over 2. Let's see, did I keep in the Jupyter notebook, I think that I kept the frequencies up to, where do we calculate the frequencies? 0 up to integer of L over 2. All right, that's good. So we'll stick with 0 up to the integer of L over 2. There we go. And then we just return the features and the labels. All right, so that's a lot of steps, right? That's a lot of steps this time, but all of those steps are things that we've been doing for the last 2 lectures. The idea is that you should ideally be learning something from each of the lectures, and so you should be able to calculate those steps once you've seen them before in the past. Let's try running the first homework. All right, so we want to look at the get features, and we see, oh, I put in a typo. The closing parenthesis doesn't match, so let's fix that typo. Which line was that typo in? That was in line 38. Going to line 38, we see that we have a curved parenthesis, a square parenthesis, a curved parenthesis, a curved parenthesis. All right, let's check the syntax again. Now I've got an expected else after an if operation. Oh, because I put the if before the for here. So I want to take the for and put that before the if I want to. This is one of those tricky things about Python where we just have to be careful about what is the syntax for the particular kind of list comprehension that we're using, right? I want to take m for m in the range from 1 to the length of the VAD, if the VAD of m is equal to 1 and VAD of m minus 1 is equal to 0. So that's just getting the syntax correct for that kind of list comprehension. All right, now it says that I've got the syntax correct. Now let's see if it will actually calculate the features for me. Float object has no attribute fs. Oh, because I did 0.02.fs instead of 0.02 times. Here we go. This should be a times. All right, so let's try running that again. X is not defined. Of course, X is not defined because the input is called a waveform. X dot shape, which row is that? It says that that was in row 32. All right. Labels, we want that to have as many features as X dot X frames has rows. So there will be as many labels as there are rows of X frames. All right, so we've got labels equal numpy zeros, X frames shape. Let's go ahead and try that. Okay, it looks like um, obviously I've not created the features correctly. Attempting to set identical low and high features. All right, so I'm not doing something correctly. I've got the VAD window length and window skip, the X window length and window skip. I'm creating a waveform from X to M to M plus VAD window length for M in the range from 0 to length of waveform minus VAD window length, VAD window skip. Those look like the right claims. And then we square the VAD frames and take the sum along each row. That is energy, let's make this an if statement. One, if energy is greater than 0.1 of the max energy, else 0. And let's turn that into a NumPy array. 1, if energy is greater than 0.1 times the maximum energy, otherwise 0 for m in the range up to the length of energy. And then start frames is equal to m. Let me go ahead and print out the start frames and the end frames just to see if it's got reasonable results up to that point. Let's do a little debugging here. We'll go back to where we run it and have it print out the start frames and the end frames. It looks like it's got 5 start frames and 5 end frames, so that part of it is doing well. What else is not doing well? We've got labels equal to numpy zeros up to the number of frames. And then for each of the start frames, we take labels from 5 times the start frames up to 5 times the end frames. Let me print out the labels and see if the labels look like they're reasonable. Nope, all the labels are zeros. And so this code is not working for some reason. It's not correctly choosing each of the start frames and each of the end frames and setting it equal to k. And why is that? It got the right start frames and it got the right end frames. Let's have it print out what it's doing here. It says that it's setting them to values, to values 0, 1, 2, 3, 4, but it's not. Oh, because start frames, this is a sample in the waveform. That's the reason. Okay. No, that's a VAD sample. That's a sample in the VAD. And the VAD is being calculated with a 10 millisecond frame. And let's look back at what we did in the Jupyter notebook just to see what it is that I'm doing incorrectly here. Um, let's go ahead and copy this from the Jupyter notebook and see if we can figure out what's different. So the Jupyter notebook, we have 0.004, 0.002. Oh, that's why. Look at that. I've got completely the wrong spectrogram size. That might have caused it. And also the MSTFT for the features should have the waveform pre-emphasized. So I should be taking this waveform and subtracting. I should be taking the waveform from x of m plus 1 to x of m plus 1 plus window length and subtracting from that the waveform from m to m plus window length. I should be doing this pre-emphasis thing in order to make sure that the high frequencies are emphasized. All right, I think that's everything. And now let's check the other part of it, the VAD part, and see if that's correct. Let me copy in the VAD. We have the VAD, we use the frame length is 0.025. The frame skip is 0.01. The energy is the sum of the square of the speech of the VAD frames. The VAD is 1 if the energy is greater than 0.1 times the max, else 0. The start frames if VAD of m minus 1 is 0 and VAD of m is 1. Yep, so all of that looks like the same. Oh, and the label goes from 5 times the start frames of num minus 1 to 5 times the end frames of num minus 1 plus 4. So we want 5 times the start frames of k minus 1 up to 5 times the end frames of k minus 1 plus 4. Let's enter that in and see if we can figure out from there if that's got everything. All right, let's scroll down and see if those repairs have fixed this get features function. It still doesn't have the right spectrogram. It has the right training labels now, but the spectrogram is being calculated incorrectly. So let me just go ahead and copy the previous spectrogram code. Let me just take this spectrogram code and copy that. Rather than trying to do this again, let me copy in here the spectrogram code. And now the spectrogram will be called features. And I don't need to print the labels anymore. So I'll get rid of this print command and get rid of this print command. And now the input will be 0.004 times fs, 0.002 times fs. Instead of speech, the input is called waveform now. So let me change this to waveform. And then I should be able to just return the features and the labels, and that should give us the working spectrogram. Let's try that again and make sure that that works. Let me zoom down to homework assignment part 1. X frames is not defined.
这个语言吗？对，我的印象应该是做了的，真的没印象。做完即失忆。すいません、先生。
Hi. Let's copy L and S up here, and then we'll call this X frames. Let's make sure that that's got the right closure parentheses and all that. Okay. And then now we know what X frames shape 0 is. So now we can calculate the magnitude short time Fourier transform is the absolute value of the FFT of the frames. Just fixing up this code a little bit. I think that that's going to take care of it. Let's try it and find out. Ah, there we go. So basically, take the things that we did in the first part of this Jupyter notebook and copy them into homework 1. I think we're going to use the same technique for homework 2 and homework 3. In homework part 2, we want to train the neural network. And so that's going to take an input features matrix and an input labels vector and an input number of iterations. Let's go back here and just copy the code from the neural network training. So the neural network training involved creating a model and creating a loss function. Here's the model. So under trained neural network, we have to first of all define a model. And that's going to have a layer norm, which is an input of 16 and an output of 6. Let's go ahead and say that n frames and feet is equal to the shape of the features. And that will allow us to say that the input here is n feet. And then the number of classes will equal to the max of labels plus 1. That will tell us the number of distinct classes. So now the input to the neural network is n feet, and the output is number of classes. All right, now that we have the model, now let's just copy the training code. The training code defines a loss function and then runs the optimizer on that model. So we have the loss function is cross entropy, the optimizer is atom, for t in the range up to number of iterations. We should calculate the 0 output, the loss values, do the 0 grad on the optimizer, and then calculate the optimizer step. And then we should return the model and the loss values. So let's return the model and the loss values. All right. So there's a lot of things, a lot of steps. Basically, we're doing exactly the same model that we did in last lecture, but we're doing it with PyTorch, which means all of this complicated, ugly syntax that is necessary in order to use a really advanced toolkit. Right, there's something bad has happened here. We want to train with the features and the labels for 1,000 iterations. It didn't like my n feats and n classes thing, so let me actually just go ahead and change that back to 16 and 6. Let's see if that solves the problem. sgram is not defined because the input is called features now. So where I had the input as the S-gram, now I want the input to be the features matrix. Let's go ahead and try running this again. Now it looks like it's running. Oh, now we got it to run and we got the loss values to decrease. So now we're basically taking the neural network training and we're training it so that its loss values decrease. And now we want to test the neural network. And again, let me go back and just copy the test code up here. The test code is going to be the test results are just taking the model and applying the model to the torch tensor of the test spectrogram. So the test neural network, the input will be the model and the features. So I want to create the test results by taking the input features and applying the model to them. And then I just want to return the probabilities are the model output transformed by softmax, detach, and numpy. So I want to take the output and detach it and numpy it. So I want to return test results, pass through softmax, pass through detach, and pass through numpy. All right, I think that's everything. Let's try that and see if that gives us good results in the Jupyter Notebook. There we go. So it is creating ASR output probabilities. Looks like we probably want to make this a tight layout. There we go. There's this test spectrogram and the ASR output probabilities. Let's test it with the grading code and make sure that everything works. Pi sound file failed. But it did run and it got 66%. Okay, let's go ahead and call 66% a pass. Let's if you get 66% here, we'll call that 100% for purposes of this assignment. I'm not sure why Pi sound file has failed on this. Oh, because the grading code didn't like Librosa. All right, let's go ahead then and check this in using GitHub. So we'll check in homework 10 and push it to origin. Takes a while to push that to origin because it's a large file apparently. There we go. Now let me go to my GitHub account and make sure that it shows up there. Switch to my student account. Go down to lecture 10. Look up homework 10. And there we go. There's everything. So we'll go ahead and copy that URL and go to the course homework, the Canvas page. Look up homework 10 and you should be able to copy in the URL of your homework 10. I'll check it to make sure that you've managed to get everything to at least the level that we've described here. All right, that's all for today. Let me go ahead and stop the recording, and then let's take attendance. Let's see, let me go to Campus Plan web menu and sign in here. I'm sorry, am I still recording or am I not recording anymore?